Okay, so before we start tackling some verifying trig identities problems that involve the Pythagorean identity and some more advanced algebra techniques, I just want to go over some of these guidelines for verifying trig identities. The the only way to really get good at trig identities is to just do them. It takes a lot of practice. It can be very frustrating. They're like puzzles that you have to put together, and you don't always see the pieces that you need. So that's why initially our practice is a lot of put the steps in order problems, fill in the blank where your step is given and you give a reason, or your reasons are given and you provide a step. We'll kind of build up your ability levels and confidence until you get to the place where you feel more confident with them. But as you're working through them, if you get frustrated or stuck, just read through these guidelines for verifying trig identities from the textbook and see if any of those are helpful for you. So the first one, number one, is to work with one side of the equation at a time, starting with the more complicated side first. And we talked about that one before. Step number two, this one is new. We haven't looked at this one yet, but we will in this next example. So look for opportunities to factor an expression. Okay, so if you see anything that's quadratic, for instance, or it's in a quadratic form, you might be able to factor it using the factor box. Maybe it's a perfect square trinomial or a difference of squares, sum of cubes, something like that, some factoring pattern that you recognize. You could also try adding fractions, getting a common denominator and combining things. You could try squaring any binomial terms, or create a monomial denominator. Okay, so um, keep an eye on step two for some of those advanced algebra techniques. Then step number three is to look for an opportunity to use those fundamental identities from your trig hexagon, noting which functions are in the final expression that you want, right? You want to always keep the end in sight because that's where you're headed. Sines and cosines, those pair up well, as do secants and tangents, cosecants and cotangents, because you can use some quotient identities and cancel things out easily. Okay, step number four, if these preceding guidelines, steps 1 through 3, aren't helping, try converting everything to sines and cosines, right? If you have anything that's a secant or a cosecant, use a reciprocal and change it to a sine or cosine. If you have a tangent or a cotangent, use a quotient identity to change it to sines and cosines and work with it in that form. And then step number 5, this one is really important, and that's keep trying something, right? Even if that path doesn't ultimately get you where you want to go, it does provide insights, and you're gaining more knowledge, more experience, more confidence with these identities the more you go. So you want to just keep persevering, pushing through that problem solving until you get to the end of your identity. Okay, so let's take a look at example 3. And this one we're verifying using Pythagorean identities. So we'll go ahead and make a trig hexagon here to help us remember our Pythagorean identities and our fundamental identities. So left vertex gets tangent, then we have the quotient identity, so tangent is sine divided by cosine. Then opposite the cosine is its reciprocal secant, opposite sine is its reciprocal cosecant, and opposite tangent is its reciprocal cotangent, and then we always stick a 1 there in the middle. Okay, so our Pythagorean identities, sine squared plus cosine squared equals 1. 1 plus cotangent squared equals cosecant squared, and tangent squared plus 1 equals secant squared. All right, those are the 3 parts of the hexagon, right here, here, and here, that draw our attention to the Pythagorean identities, which we're going to want to keep an eye out for. So when we look at our given information, we want to prove that the cosine fourth of x minus the sine to the fourth of x, that quantity all divided by sine squared of x, is equal to this right side cotangent squared x minus 1. And the more complicated side is where we start with our given, and that is certainly in this case going to be that crazy looking fraction. So cosine to the fourth of x minus sine to the fourth of x, all divided by sine squared of x. Okay, so that's where we're going to start with what we're given, and then at the end we want that to match the cotangent squared of x minus 1. So that's our goal. That's where we want to end up in the last line. Okay, so looking at this list of guidelines again. It says work with one side at a time. We did that. Next, step 2, look for opportunities to factor an expression or add fractions. So when we look at this numerator here, we have a cosine to the fourth minus a sine to the fourth, and that's a difference of squares. So if you recall from algebra, a real basic difference of squares might be something like x squared minus 4, right? Those are two perfect squares, so we would factor that into x plus 2, x minus 2, because with this shortcut for difference of squares, you square root the first term, square root the last term, and then the factors get opposite signs. So if we try that with this cosine to the fourth of x and this minus sine to the fourth of x, that's going to need to square root the first term. So the square root of a fourth power is a square. So we'll have a cosine squared of x. Then same thing for the second term. We're going to square root that sine to the fourth of x, and that'll give us a sine squared of x. And then one of them gets a plus, and one of them gets minus. So that'll be my plus, and that'll be my minus. And then that's all divided by sine squared of x. Okay. So that we went from the given to factoring a difference of squares. Okay, now the next line tells me in the reasons column to use a Pythagorean identity. And when I look over at my trig hexagon, I am reminded that the sine squared of x plus cosine squared of x is equal to 1. And that's what I have right here, sine squared of x plus cosine squared of x. So that term is going to cancel out, that binomial, and leave me with just a 1 using that Pythagorean identity, and 1 times anything is itself. So I'll have cosine squared x minus sine squared x, all divided by sine squared x, using my Pythagorean identity. Okay, now you're tempted, everybody's tempted, to cancel those sine squared x terms out of there. You cannot do that though, because this is a binomial in the numerator and this is a monomial in the denominator. So we don't have factors. We can only cancel common factors, not common terms. Now we're going to look down at our next reason, which tells us to split one fraction into a difference of two fractions. So this binomial in the numerator here, we're going to split that apart and put it over that common denominator. So cosine squared of x is going to be divided by sine squared of x. Then that's a subtract, and the next term there is sine squared of x, and that gets divided by the same denominator, sine squared of x. Okay, so we just split apart that one fraction into two, and the sine squared of x divided by sine squared of x, that's just 1. Any number divided by itself is 1. So we'll have a minus 1 here. And then cosine divided by sine, if I look at my pentagon for remembering trig identities, here's my cosine, here's my sine, and remember that division, the quotient identities, are the ones that have consecutive vertices. So a cotangent function, cotangent would be equal to cosine divided by the sine, right? So since cosine divided by sine is cotangent, I can change this cosine squared x divided by sine squared x into the cotangent squared x. And then I have my minus 1. And when we compare that to what we were looking for up there at the beginning, we've done it. We've verified this trig identity. Okay, so hope that helps, and go ahead and try the checkpoint problem on your own.